get it. Okay, so welcome everyone. This is really exciting. The objective of today's session is to show you how to go from zero to hero, or how to run Clay. So we will start just saying who we are speaking, who are you speaking, or who we are. And then we'll jump into Daniel is gonna do a really run through the most basic version. Then Soumya is gonna do the application for different tasks. And then we will go into a little bit more background of what is Clay, how we set up the organization, and then we go into the code and all questions. This is a very relaxed session, and you should be watching this on YouTube, and the chat should be activated, and you can just ask questions there, or if not, you can email us, for example, bruno@madewithclay.org, and then we'll get those through the live. So my name is Bruno Sanchez, Executive Director of Clay, and really excited about this. Laura?
Hi, I'm Laura Chen, and I'm Clay's Chief of Staff. And yeah, super excited. Also, if you're non-technical and you're looking for that kind of session, we have those sessions as well. And so you can sign up here, dropping this in the chat. Not dropping it in the chat, drop it in the YouTube chat. And you can sign up at madewithclay.org/demos if you want a more non-technical session. Daniel, you want to go?
Yes. Hi, I'm Daniel Wiesmann. I'm a product owner at Development Seed. I've been working very closely with Clay in developing this model, and feel very attached to it emotionally and work-wise. Great project. Super excited to present it together with Clay, our partner.
Soumya?
Yep. Hey everyone, I'm Soumya, and I see we have one attendee now, which is Rahul. So Rahul also worked on Clay Textual. So I work at DevSeed. I've been a part of Clay for more than 6 months, 8 months now. Heavily invested on the model side. Really like what we have built and what people are doing with that. Yeah, looking forward to today's session.
Yes, so what we are using is, we are in a Zoom meeting that is being broadcasted on YouTube. So that's why Raul, which is from the team, if you want to jump in, Raul, let me know, and we'll just jump in too. And if someone wants to demo something quickly, we can also add you to this webinar, and then you can demo things. But otherwise, most of you should be watching this on the link on YouTube. So the first thing, let's just go straight to it. I will be making notes of concepts that maybe need some explanations, and Daniel and Soumya, feel free to explain some of those, but I like the idea of just throwing ourselves into the practical way. Okay, let's start doing the thing. Maybe we need to start a server, so maybe we're going to start with that and then do the fine tuning. Is that the first thing, Soumya, we want to do? Okay, so let's start from really scratch and spin up a server.
Yes, exactly. So here we are in the console of AWS, and we can we'll really start from this button here of launching an image. I'm going to call this webinar 1, and usually we use a pre-built PyTorch image, Ubuntu based. That's what we use mostly, but I mean, there's no obligation in using this at all. Any of the instances work as long as you can then install the libraries on your own. But this year comes with batteries included. I think we'll have to convince AWS to install Clay in there as well eventually, but for now, like, I think this is the instance type, and we will use one with the GX2 large with one good GPU and some good memory. Is what we usually use. And I think that's it. The other thing here is I'm going to use a key pair that we have pre-downloaded, so I have this already on my computer. But you can also create a new one while launching the instance, and then you should be able to SSH into the instance as soon as it's live. So this is pretty fast, usually, I think, because these are like fast instances, so they spin up quickly. You can then go here and get like some instructions on how to connect. I'm going to use an SSH client through Visual Code. So I'm copying here the entire SSH command. I'll have to update the link to the key file. I think now I need to share another window. So let me unshare and share again. Go here to Visual Studio. And here, if you look for a command, you can say command here. Yes. So I have to add a new host because this is a new instance. I just copy paste it in here, and then the only thing I need to do is to update the path to where the key sits.
While you do that, by the way, there's tons of ways to do this. You can also go to the web and just directly to the browser to do this. You can also use Cursor, or you can use other things to do that.
Yeah, exactly. But this actually, this just opened. Now, when I click connect, it opened another window. So let me share that one. I'm jumping from window to window here. I think this one. All right.
Also, forgot to say, which I think is really cool, Laura is in New York, I'm in Copenhagen, Daniel is in Portugal, and Soumya is in India.
That's right. Yeah, so now we're on the instance basically. So this is VS Code connected through SSH to the instance. I'm just going to open the root folder and clone the repository. So for this, I'm going to get the HTTPS link to the repository because I don't have a key set up here. But since the repository is public, I can basically just clone without an account. So click clone, and maybe make this a bit bigger. There we go. So this downloads the repository and clones it locally. We get in there, and now here, this instance already has Mamba and Conda installed. So basically, if I look at the README, it contains the instructions for what to do. So here, the first command is to create the environment itself. This will install all the libraries that the model needs. And this is the longest step in this setup, I think. This basically will download Torch, maybe not, because that's already installed, but a lot of the libraries.
This is Mamba is a drop-in replacement for Conda. So though, if you know Conda, it's the same thing, just faster.
Yeah, exactly. And so this is kind of resolving the environment, and then we'll start install.
I use my Mac for coding, so you can also work with Mac. I don't know if anyone in the team uses Windows, but it should be the same, right?
Probably, but I don't know. I think Conda is good. Is one advantage of using Conda over pip is that it's more transportable and more stable in that sense. It's easier to replicate the exact environment. But I have no experience with Windows in setting these things up, so I don't know. About that.
I have a Surface at home, and I sometimes do code on that. So Windows now has something called WSL. So there's WSL2, which is Windows subsystem for Linux. It's very well built. Like Surface is not designed to do like high-end programming, but I always like find it super easy to like spin up an Ubuntu instance, connect to it. It connects to GPU. It connects to your Docker instances and runs like I have tried running Linux on Windows since I started my engineering, and I think now it's with WSL. That's like the perfect way to run Linux inside Windows. So if you wanna do programming and build models, I'd recommend using WSL rather than doing it natively in Windows.
Oh, so, Daniel, can you show the GPU that this machine has to just show the people? We've used it with consumer grades. Like I have a 4090 NVIDIA and it was amazing, obviously. And the M1 on my Mac, it works slowly, but it works. Somi, I think you have a different GPU, right?
Yeah, I have a 3090. Yeah, it's like less powerful than 4090, but does the work.
And the training was done on, was it H100, right? In 32
Yeah,
H100s.
P5s. Yeah.
Cool.
Yeah, just still installing a few things. For instance, here it has an NVIDIA A10G. It has 23 gigabytes of RAM, which is pretty nice. Locally, I have 8 gigabytes of RAM, I think, on NVIDIA RTX. But it also even works for little tests. So the notebook I'm going to show also works really well on CPU because it's
Yeah,
just a little
true.
data. And it takes a few seconds and maybe instead of a few milliseconds to make some of the inference. But if you're just doing an example notebook like this, it works. Or even if you have a few hundred images you want to process, it still works pretty well, I think. So,
Do I remember correctly that one mini batch, so one run on a GPU is less than a second, but on a GPU, on a CPU was like 8 seconds. Of course, it depends on which ones, but roughly rule of thumb, it's at less than a second, like maybe even 200 milliseconds, and maybe like 5 seconds or so on a CPU.
yeah. But so while this is installing like the notebook we're going to run is here in Docs tutorials. There's the Clay V1 wall-to-wall notebook that is the one that we're going to run first. It's a very simple example, but it downloads imagery, it loads the model, it makes some inference, and it makes a little bit of analysis on the inference as well. And so it's a kind of, that's why I call it wall-to-wall, because it really shows from image downloading to inference and analysis. It does a little bit of everything, and so it gives you a good overview of one way from another. And then the other thing is you can, with this install, it will install Jupyter Lab. So now I think I still need to do conda init because this is a fresh machine, so it will source this file. So this is just to set up Mamba properly, and then I can say Mamba activate model. Here we are, and now we're set up with the environment. So now we can just go to Jupyter Lab, and it was no browser, right? Because this is on a remote instance. We want this to kind of make a connection such that we can use it locally. And I believe after that we can open this link. And then now again I have to change window because now we jump back into the browser. And now we have a Jupyter Lab that is like get from the remote instance.
Which
basically,
you could have done this on a normal terminal and then join in the browser, which is the same thing.
exactly. It will look exactly the same. Even here, the address is now localhost. So this is ported to the instance, but from here on, it really I could be running this on the machine. It's basically, you wouldn't really notice the difference except for maybe speed, right? Like if you If you don't have a GPU, then you might notice some differences to run this remotely.
Yeah, so this is
yeah.
not localhost. You piped the port 888 from the remote to your localhost. That's
Yeah, exactly.
the
This is
difference,
definitely,
yes.
yeah. So this is running on the remote machine now. Okay, so this is the notebook here. It's opened, and the first thing, like this is something I'll probably do a pull request today. Because while testing this, I realized that this we usually append the home directory of the repository with the system path or the Python path, such that it can be detected and you can import things. And this notebook used to live just one folder down, and now it's two folder downs in the tutorial subfolder. So we'll add like 2 levels down of folders, and then hopefully this import will work, because like this source.model is what will be locally installed or imported from the Git repo itself. Okay, so now we're set up. We're able to import all the libraries we'll need for the notebook, and the notebook is annotated, so and you can also, when you run it, you can kind of follow this again. But we basically do set the location of interest, download some imagery, then load the model from the checkpoint. There's like 2 different ways to do this, and then we prepare the data itself in a format that's maybe the most technical part, in the format that the model needs. Then we can pass the imagery to the model, create embeddings, and then we do a very simple analysis of the embeddings themselves. And so here, actually, maybe also let me zoom in a little bit. Is this a good size? Okay, so if it's too small, let me know. But yeah, so basically here, this is a lat-long location over Portugal. And these dates here, around 2018, like early fall, there was a big forest fire around this location. So we set the date, the range, and the location, and then here we use Stack and PyStack, the library, to access Sentinel-2 imagery through a Stack catalog that is maintained by Element 84, which is very convenient. So basically here, the first part is to do a search and list items. So for the date range, with some color filter here, we found 12 items, which means 12 different Sentinel-2 scenes, 12 different dates. And then what we do is, this is basically a bit of convenience. So we specified only a lat long, but now we need to create a bounding box around this lat long to tell Stack what piece of the imagery to download. And so this is basically just projecting the point into the coordinate system of the images that we accessed, and then creates a bounding box of 256 pixels at 10-meter resolution. The resolution here is basically defined through the projection of the original of the satellite imagery itself. So this is just creating a bounding box. And so here, if you look at this, bounds will just be a bunch of coordinates in the projection of the imagery, right? So this is not lat long anymore. This is already projected, and you can see that if you subtract this number from this number, it will be 256 pixels times 10, so 2.56 kilometers. Okay, so this is setting up the items and the bounding box, and then using another library called StackStack. In just a few commands, we can download the imagery itself. So here, this actually goes in, and for each asset, each of the bands for each of the 12. Actually, it's not all bands. So we use 4 bands here: red, green, and blue, and the near infrared channel. For these, it will download the data. So it creates an X-array for the 12 time steps, for the 4 bands we specified, and for the pixel size of our bounding box, which is just 156 pixels. So I mean, this can be extended to other bands if you want, or reduced, whatever is useful. So here this is kind of flexible. Okay, And so this here is a kind of a hack for the notebook to keep it small. We copy pasted the imagery and made a link. So this here is a markdown cell that shows you the imagery, but now we just plotted the download of the imagery we did locally. So here you see the time series. There's two images that have still quite some clouds in them. And then there's 5 images that are before the fire, and then 5 images that are taken after the fire. You can clearly see visually, like these gray areas are the areas that have been burned by, those are burn scars from the forest fire. Okay, so now we have, like if you look at this, put this, if you say stack, this is the X-ray, we have the data in here. So until now, what have we done? We've basically downloaded some imagery and put them in an X-ray /NumPy format. And now we're going to load the model and convert this X-ray into the format that we need to pass it to the model, because the model doesn't directly accept X-rays. We have to do a little bit of work around that. I think this is also something we might tackle in the future to make this easier. Okay. And so here we can load the model from a checkpoint. I'm using one from S3, but you can also go to Hugging Face to download. And then the model also comes with a metadata file that actually, does this also need to do like this? Let's see. The metadata file has information about bands, for instance, and wavelengths, etc. Because the model is pretty flexible in what it can take as input, so we have to specify for each of the bands that we selected for these arrays. We have to tell the model not from what satellite it is, but what the central wavelength is for each of the bands we use. And then
So
normalization.
Well, it allows Daniel also to say that the model, the checkpoint is 1.6 gigabytes, but that's the whole model with everything. So you could continue training the entire thing with that checkpoint. In fact, here we only use the encoder to make the embeddings. So probably the things you use might be half the size. We have not yet, as of the recording of this live stream, we have not yet recorded a checkpoint with only the encoder size part, which would be maybe half the size.
Yeah, and so then once it's downloaded, it will instantiate the model here from the checkpoint, and it will hopefully use this metadata file. Since this is using a relative local path, and I added this, I hope you got this right.
Yeah, it happened to me sometimes that I put the wrong path and I only get that message after it has, after I waited for the model to download.
Yeah, exactly. Let's see. I think I got it right. But
Worth saying while you do that Clay can work on any instrument on any wavelength. You might need to put the specifications, and hopefully there's time today to do that. But that's one of the key features of the model.
yeah, so the model is instantiated. We can print content here in the console. It's meaningless, but it just shows, okay, this works. And now, basically, the model doesn't know about satellite systems. It doesn't know Sentinel-1, Sentinel-2, Landsat, or whatever. You basically pass wavelength and then normalization parameters to it to tell the model what it is. It's been trained with Sentinel-2 and Landsat and high resolution imagery from NIPE and New Zealand. NIPE is the US. So these are already registered in this metadata file, and they're like known wavelengths to the model. If we go out of this, it should still work, but it's just not being trained with the data. And so here, basically, what we do is we create these lists of the mean value for each band, the standard deviation for each band for normalization, and the waves are the central wavelength for each band. So here, you can look at this, should be a length 4 array. So these are wavelengths. These are the mean values for each of the bands. Okay, so the model is going to use this for normalization. And so similarly, the date and the location of the image are passed to the model, but they have to be normalized, I would say. I don't know if normalizing is the right word, but they have to kind of put into a standard, more machine-friendly format. And so these two functions here, they will basically take a lat long or a date stamp and convert them to
yeah, so these are design choices we made for Clay to not give the day itself, but to give the time, the week, and the normalize to that, to these changes. This is something we can and we should wrap somehow to make it easier. But yeah, this is just this. Probably this section is the one that is more specific to Clay, more finicky.
Yeah, but it could easily be abstracted. So
yeah,
the thing we want to work on eventually is to make this way simpler, such that people don't have to worry too much about this, including ourselves, right? Like when we run this over and over again, we don't want to reuse this boilerplate code all the time. But so as an example, if you look, these are normalized values of the longitude in this case. Okay, now we're ready, so we can make a data cube. The data cube contains all these values, the platform. The model will use this internally to look up some wavelength, but this is also something that the model doesn't necessarily need in that way.
This is the actual input. So we have all the data already, we have all the parameters, and we just basically need to package it to give it to the model.
Exactly. So, and that's a dictionary for platform, time, lat long encoded, and then the pixel values normalized. And that's it. Yeah, the ground sampling distance, which is 10 meters, and this here are the central wavelength. Okay, so then running the model, basically it's this line here where we give this data cube to the instance, and then this one basically extracts the class embedding. So we have a bit more. We have like 207. We have patch level embeddings if we need those. If you want to access those, but we don't really need them here. The embeddings are basically single arrays of 768.
So it took a little bit more, and I think it's because the first time you run it, it needs to load into the GPU memory, the model, right? If you run it again, it shouldn't take that much.
I don't know. Let me try. Yeah. No, it's fine. And so now for each time step, 12 images, we have this embedding, like the length of the embedding output. And so
we'll explain what embeddings are in a second, but this is basically a summary, mathematical summary of the image.
Yeah. And so here, this cell does a principal component analysis of this small array. The idea here is to say, okay, like find groups, find like different principal factors. And so here we're just plotting this single principal component, and already knowing how the output looks like, we colored the images, the points manually, such that they're even easier to interpret on the graph. So these two green points are the cloudy images, the blue points are the images before, and the red points are the images after the fire. So if you see like the first and the third image are cloudy, so up here, the first and the third one are cloudy, they stand out compared to the others. And then there's like a systematic difference between these 5 and the last 5. So this is basically just showing these embedding vectors. If you reduce each one of them to just one single number, this one single number kind of varies pretty clearly depending on what's in the image. Okay, and so the fact that these are all more or less at the same level, and then these are another level, and the two cloudy ones jump out even more, means that within the embeddings, this information of the difference is encoded. And so basically this difference can also be picked up by a very, very simple classifier. This is a toy example, obviously, just a few observations. But to make a point or show how this could work is we basically label the images. So again, the first and third are cloudy, and then we have before the forest fire and after the forest fire. So this is like a little encoding of the label for each image. And then we split them into a fit and a test set, both tiny, but again, this is more like for instruction. And we can train a support vector machine model that fits on the labels for the for this fit set, training set, and then make a prediction on a few other embeddings it hasn't seen, so to speak. And if you just run this, again, this is tiny, but based on these 5, it's able to also predict the other 5. And in this test set, we included 1 of the cloudy images, 2 of the before, and 2 of the after fire. So it gets all those 5 labels correct. So it's just an example. This last piece of this model, imagine you have several thousand examples. Then basically this support vector machine model, this tiny model would take as input an embedding, which is the simplification of the original image. And then based on this embedding, make a prediction on what's in the image, if it has a burn scar or not. It is, for example, it works really well. Yeah. And so again,
Thank
this should
you.
be run on your machine, and it should also work on CPU. If you don't have a GPU, you can try it out. Since this is just a little bit of data, will still be pretty interactive.
Thank you, Daniel. So this is a perfect example just of how to download the model, how to read, how to create embeddings, and how to operate with them. It's not the point is not to show the performance of the model, just to show, hey, how do you read, how do you run this thing? Now is the thing that probably most people want to know, which is Soumya's time to shine, which is to show an example of how you do, we're going to do, correct me if I'm wrong, Soumya, regression example, classification example, and segmentation example, right?
Yep.
Take it away. Thank you, Daniel.
Let me share my screen.
So Mia, do you want to just really quick explain or go over what an embedding is and what we mean as when we say fine tuning in this context, just so anyone who's less familiar can be on the same page here?
Sure. So embedding is nothing but a compressed version of your input. So in case of images, we have a lot of data, and based on what model you're using, each model has an embedding dimension. So in case of clay, the base model that you have that generates embeddings of size 768. Now each vector of the 768 represents a certain feature. So this is a cool experiment that you can try, which I think we did when we were building the text to earth version of clay. If you actually visualize the clay embeddings or any embeddings per se, they look more or less similar. Like given different places, different regions, if you look at the embedding, they look like to humanize, they look more or less the same. But internally they are different. Like there's the small fluctuations in each of the embedding vector that represent that feature. And that kind of stands out, and that's how they're differentiated. And the difference between pre-training the model, like a foundation model, and fine-tuning it is when you're doing pre-training, you generally are training the model for an auxiliary task, right? Like, and in case of in Vision, there are basically 2 families of this task. One is the mask image modeling, where you mask out or you remove like certain section of your input image, right? And your task then is to reconstruct it back. That's one family of models. The other family is contrastive, right? The clip family, where you have pairs of input, like let's say you sample 2 points and you sample 3 points, 2 are from the same region, the third one is from a different region. Then you use augmentation to modify all 3, and then your auxiliary task is like 2 images that are from the same point. They should be closer together in the embedding space, while the point that is from a different region, it should have a different embedding space, right? So you try to move images that are similar closer together in the embedding space, and images that are not similar. You try to basically pull it apart.
Can you
From
unshare screen really quick? Just then I can share visual that goes with this.
Sorry, I didn't realize that. Yeah, yeah, and from what we are seeing lately in the past 2 or 3 years, it basically, I think a lot of the momentum is towards the mask image modeling style, and that's what we have used in Clay. We are using mask image modeling as well. Yeah, so during pre-training, you solve for this task, which is an auxiliary task, not something that's the actual task. During fine-tuning, you freeze the model, so you freeze Clay. You're not training it anymore. Instead, you attach components or layers on top of Clay that is suitable for your downstream task. Now, for something like classification, it's very simple. You take the encoder, you get the embedding out of it, you attach a linear layer on top of it, and you're done, right? Based on how many other classes you want to detect, your model should be able to do that, and it should be able to do that like fairly quickly rather than taking a lot of time. For segmentation and regression, like for segmentation particularly, it's a little more involved, right? Like the segmentation is in the input image space. Now imagine what your encoder does, right? Encoder takes your image, which is let's say 100 by 100, so it has 10,000 pixels, and it encodes it to let's say 100-dimensional vector. So 10,000 pixels are now encoded in 100 pixels. Now you have to reconstruct the input space back. So generally for these kind of problems, we use like something like a unit kind of architecture where you have like residual connections for intermediate layers for the model to have an understanding of what the input space actually looks like and learn intermediate features. The problem with transformers, and particularly the VIT style of transformers, is it reduces your input space from the first layer and then it keeps constant, right? Because we use a concept of patching where you take an image, you split it into patches, and based on how many other patches you have, your resolution is reduced by that much. Typically, it gets reduced by 32 or 16x the input space, right? So that's the resolution that stays constant throughout the transformer. That's not the case with connets, right? Like a unit type of architecture. So we had to do like some tweaks. So whenever you do a segmentation or a regression, like a more involved regression, like per pixel regression, we'll see a few examples of that. Then you need to extract intermediate layers of the transformer. You need to reconstruct the images at a higher resolution, create your feature pyramid network, and then build a decoder on top of it. So that's a little more involved, and there are like multiple ways of doing it. There's a good paper called Scaling Up to Scaling Down that basically lists down all the techniques like adapters, LoRa, child fine tuning, and other ways in which you could take a VIT kind of pre-trained foundation model and use it for your downstream task. So I recommend you go through that. I'll attach the link to the paper as well.
So one of the, Somi, if I may, 1 second, if I'm making a square, I don't know if people can see it, but in the top bottom right corner, there's an example of an image of a plane field, and then below that is the embedding of that field. And what I like of this example is that a human would see this and then would not maybe see that much that shadow in here or the structure around it. But the idea of embeddings is that they're able to convey the semantics, the things that are in the image in mathematical terms, in numbers. Like for example, in this other example, well, let me put the, I can do here. I don't know why. There you go. In this other example, or the trees, each tree is a blob. The idea is that not only there is a blob here, but the visualizations of the numbers are a little bit limited. The idea is that then the concept of a tree or the concept of a road or the concept of a house or deforestation, all of these things become numbers. And we are really good at managing numbers. It takes milliseconds to query a database of numbers. And that's the revolution of AI for Earth, is that if you can embed the thing, then you can work at mathematical speed, at numbers speed, not at concept speed. Like otherwise, you would need to do a computer vision for each of the problems and then find the lines and find the squares. And in this case, all of that pre-work, all of the work ahead of ahead of doing what you actually want to do, it's done by the foundational model.
Yeah, and another thing that I want to point through, these are really good slides. Daniel, can you go to the previous one where we show the embedding space? Yeah, so this is basically, so when I say, right, like each vector in an embedding, right, in case of clay, we have 768 vectors. So each vector represents certain feature, right? In this case, like we are just seeing 120, but there are 768. Now, some are visual, right? Some are very evident. Like if you look at feature number 97, you can clearly see it partitions land and ocean, right? Or it maybe is an edge detector or something like that. Similarly, if you look at image feature number 102, that basically like detects beaches or lower like water regions and stuff. So each vector in the embedding represents one feature, right? And you can take that and do things with that, like with one single vector alone. But that's a little tricky to know, like, because not everything is visual or evident visually, but it has some internet like underlying meaning to it. So in the next slide, what we do is we pick one feature, like I think we are picking feature number 97 here. So if you go to the next slide, Daniel. Yeah, so we pick feature number 97 and we try to use that filter on all these images. So you see the first rows are the images, the second rows are the embeddings that get created by Clay, right? So you can see like by default, like without doing anything, this can be used as a segmentation task, right? Like because it detects like edges, roads, rivers, trees, and like a lot of the patterns are kind of evident. Now, we didn't train the model for this particular task, but because the way it is trained and the auxiliary task is to reconstruct the input image space, it understands these features for it to do that task properly.
Cool. Let's go to the examples, and then we can either do Q&A or we can tell you more about the organization Clay, what we did this, why we did it as a nonprofit, blah blah. But for now, let's continue with application. Show me up with all these types of regression, classification, and segmentation.
Well, let's start with segmentation first, and then we can go to regression and then end up with classification. I'll share my screen again. Do let me know when you guys can see my screen.
Yeah, we can see you. We can see it good. I think the resolution of the text is good, but if you can make it a little bit bigger, then even better.
I made it a little bit bigger. Is this good or shall
I think it's good,
increase?
but hopefully, otherwise, YouTube people will tell us in a second.
Cool. Okay. So the first problem.
So this is running on another remote instance where we basically downloaded all the data that we're going to use for the examples into the instance. That would have taken too long and to be not interesting for any viewers.
Oh yeah, that's right. Can you show it, Somia? Can you just go like a little bit on the system to show the size of the data we downloaded and blah blah blah?
Sure. Yeah. We will look at the data. I'll explain like how is this instance different from the one that Daniel just created. Like the only difference is whenever you start an experiment, you need data to do it, and we didn't want to like download the data during the session, so that's why I have some data. So I'll just zoom in a little bit further so that it's more clear. So
Perfect.
let's see. We have a data repo. Now you see it has biomasters. This is a regression challenge hosted on driven data. CVPR has the segmentation data, and DS has the Eurosort data. So let's look at CVPR first. So CVPR, so that has.
And all of those data sets can be downloaded.
Can be downloaded. So if you
we can put the links, yeah.
Yes. No. If you go to fine tune and then segment, right? Like that's the first one we're covering, right? Let's open the README file and we'll do exactly what the README says. Okay. So So I'll open the README. So it tells you how to download the data. So you clone the repo, which we have already done. You cd to the model repo, you create the environment file, and you activate the environment, right? So this is what Daniel did, and I've done this already. So you can see I have clay model environment active, and I'm in the model repo here. After that, you need to now prepare the data set. In this case, the Chesapeake Bay data is hosted on, I think, source code, AWS, right? So you could use either S3 to copy, or I'm using S5CMD, which is basically S3, but it runs in multi-thread mode. So it does like a faster copy from an object store to your local. So you pull in your data, right? So if you see here, you pull in the data and I'm storing it inside files slash train. So if I look at my uh, data CVPR, I can see there's a files, right? And inside that I have two repos, train and val. Let's look at train. Now train has a lot of like TIFF files, which are the nape imagery of Chesapeake Bay, and it has also the land use land cover classes for these. Now these styles are a little larger. I think they cover around, these are nape tiles covering, I think around 5,000 plus 5,000 pixels. So it's not straightforward to feed it into the model. So we had to like crop it and create smaller chip sizes, something that's more relevant and easier to feed to the model without like getting an out of memory error. So there's a uh, function called preprocessed data that takes these TIFF files and creates chips of whatever size you pass, right? So I'm saying, okay, create chips of size 224. That's the native resolution at which Clay was trained on. So I'm saying, okay, take this data, create chips of size
Why,
224.
can you explain why 224 and what would happen if you make a very small number there or a really big number?
So this number is not fixed. You can make it 32, you can make it 64, you can make it 256. So the good thing about Clay is like it can take input images of any size, right? But I would limit it to like 512 or 1024, because if you go beyond that, we use a patch size of 8. So you take the number, you divide by 8, and then you multiply it with itself. That's the number of patches it will create, and that might explode your memory. So this number 224 is not constant. Feel free to like pass in images of size 100, 200, 300, 400, any number in between. Just don't pick let's say a number like 10,000 or 5,000. That would then create, the model might still work. It would create a lot of patches, but that would then throw out of memory error.
This is 10-meter resolution, so this is 200 meters, sorry, 2 kilometers
2 kilometer
by
by
2
2 kilometers.
kilometers.
Cool. So once you run the pre-processed data.py file of this size, now we can look into our data, CVPR. Now I'm specifying create a directory called NY, because this is New York data, I think,
I
and
think
it creates train and val.
this specific example is night data, correct?
Yeah, this is NAP.
Oh yeah, nape, sorry, then it's 1 meter, then it's
So this is
200
1
meters.
meter.
I was
Yeah,
like,
sorry,
wait,
this is 1 meter. So
yes, that was
yeah.
like, this is very big. So 200 meters, 224. Thank you.
Thanks, Daniel. Yeah. So under train, we have chips and labels. So if you look at chips, you can see like it has created chips of size 224 by 224 and saved it as .npy files because easier to read. And you can look at labels as well. Yeah, so labels are also like split into 224 by 224 chips and stored. This is just like pre-processing that you need to do to create your data. After doing that, your structure looks something like this. Under NY, you have train val, under which you have chips and labels. Okay, so this is the pre-processing that you need to do with your data to feed it to Clay. Now we'll look at like actually training the model. To do that, you need to download the Clay model. So you can go to the Hugging Face model repo, and here you can download the model, right? So Clay v1 based checkpoint file. I already have it. So if I show base, you can see like I have Clay v1 base uh, checkpoint file in my system. Okay, so these are things that you need to do beforehand. Then you can start training your model. Now Clay by default uses a config file And any downstream tasks that you want to train Clay on, they also are driven by configuration files, right? So let's look at the configuration file for segmentation. If you go to configs, segment Chesapeake, now this is the configuration file, right? So here we specify my training chip directory, my training label directory, the same for validation. Clay needs a metadata.yaml file. Let's look at what metadata contains, right? So it basically has information about all the sensors or satellites it was trained on. So Sentinel-2 has 10 bands. Its RGB indices are these. It has a ground sampling distance of 10 meter. These are the means. These are standard deviations. These are the wavelengths, right? Similarly, I have this for NAPE somewhere here. Yeah, so this is NAPE. The bands are in this order. These are the mean, these are the standard deviation. It basically contains metadata about your satellite or the sensor that the model was pre-trained on.
And that's where you could extend if you use a system that is there. Basically, the same structure can be provided to the model. The model doesn't really store any of this directly. This is really metadata. So if you have another source that has its own specifications, then you can put that in there. I would say probably most 4-band imagery will have very similar wavelengths as NIPE. So if you don't know, you can also basically fall back on NIPE many times, I think. So just saying this can be extended, and that's a bit the point here. Like the idea is that the model doesn't know about satellite systems; it only knows about wavelengths and resolutions, and hopefully it will work as out of the box for many different systems because it was trained that way.
Yeah, exactly. Thanks, Daniel. So next, you specify what your batch size is. Now, this is something that you pick based on
I am not hearing.
Yeah, I think we lost.
This is what happens because we are at the 1 hour. So there is a little. Somia has a little issue in his local computer that if the stream is more than 1 hour, his whole system crashes. So he will be back in a few seconds. So let's just go. It takes him roughly a minute to do that. So let's do some questions while he comes back online. Andrea was asking, hey, I saw 0.57 in your wall-to-wall example, but Somia is using from Hugging Face, which is B1 base. It's literally the same. The reason is 0.57 is not the version number, it's the loss of the checkpoint where we were training Clay. It's just the naming convention where we were training, but it's literally the same file as the B1. Right, Daniel?
That is correct, yes. So basically, I think I'm not sure if you need a Hugging Face account to download directly to put in there a link, a remote link, something like that. At least I have problems before. So at the time when I wrote the notebook, I made this S3 link that is public. It's the same file, but under a different name. But I'd like to check this with a Hugging Face link if possible. So maybe you can look into how to make this work.
So there was another question of the size of the embedding, and I think it depends a little bit on the memory, but also on the thing you are trying to look for. Like imagine the size of the embedding is like the chip size. So if you have the images on my screen and then you make a chip size like this big, and you're trying to look for faces, there's no face that fits on that chip, so it's going to be harder for it to detect faces. But likewise, if you make if you're looking to detect, I don't know, rings on the hand, and you make the size, the whole image is going to be super small compared to the size of the image. So it might be harder. So I would say my rule of thumb, if I can choose, is that the semantic you're looking for on the maybe one order of magnitude between maybe 5 times the size of the thing you're trying to look for, but it's totally something we haven't figured out best practices. But I would say that we see it a lot, for example, with agricultural plots that are circular. If the size of the embedding is it's too smaller than the circle, then it doesn't see the circularity of it. But if it's very big, it doesn't see the small stuff. So just play with it and do different ones.
Yeah, I think that's also true for applications that are around change, for instance. So the burn scar example, if we had a huge area and the burned area that you're looking at is just a little piece of the whole landscape, and there's other fields from agriculture that have been sown or plowed in the meantime, there's like other changes going on, and so the change in the embedding might represent other things than what you're really trying to find. And so I think there is the same concept.
And there's Soumya back. No worries, Soumya. We explain what happened to you. You can share the screen and continue like if nothing happened. This is live, so it's recorded. So this will be there. It's maybe incentive to fix that bug on Ubuntu.
No, it was not the Ubuntu issue. It was my nephew. So it's work from home.
Oh.
He was playing cricket and he somehow hit the Wi-Fi.
Oh, okay. Then one's a different one. I thought it was because it's also at the same time. Didn't you have a 1 hour limit on your?
Yeah. But hopefully, like I'm still alive. So let's continue.
Let's continue. Quick answer to another question. Yes, you can use Sentinel-1. You can use any remote sensing. Sentinel-1, Sentinel-2 is the ones we train with, and NABE and LINS, which is New Zealand. I think it's 5 centimeters. So yeah.
Cool. Okay, we'll continue with the segmentation task, right? So we are using a batch size of 40, and let me show you what GPU do we have. So you can see, so it has NVIDIA A10, right? So it has 24 GB of VRAM. So based on what GPU you have, if you have like an 8 GB or a 16 GB, you probably want to reduce your batch size a bit. And the number of workers is typically the number of CPU cores that you have in your system. So yeah, based on that, like pick your number of workers. In this case, we have 7 classes, right? Feature maps, we'll discuss this later. Just remember this. Which checkpoint do you want to start with? We want to start with a clay base checkpoint. We want to use a learning rate of 1 in like 5, weight decay B1, B2. Then these are standards. So we are using PyTorch Lightning as our engineering framework. So it kind of gives you this config file. So you can specify accelerator as auto, devices as auto, and it would pick if you have a GPU or a TPU. We are using BF16, like float 16. This particularly a format by Google that increases the range of values. So using that as a precision metric.
This doesn't work for all GPUs. I think older GPUs locally might choke up on this. So on my computer, I have to change this to float 32 for it to work, because my GPU doesn't like this data type. So this might be an area.
Also, it's a good point, Daniel. Like you should also check if it supports B float 16. So some GPUs, I think it's the latest generation of GPUs that support B float 16. V100s and others they don't. So if you specify this using that series, your training would be like very slow comparatively. So if it doesn't work for you, just use float 16 or stick to float 32, and that would work. Then a few other things.
The mixed thing you're using is because it's more memory efficient. It uses 8 when you can use 8 and 16 when you can use 16.
Yeah, and 32 when you can use 32. Like I think it's still the optimization another state in 32. They stay in 32 float, and also the model is always saved in float 32.
Question that I don't see there, the patch size is not, it's in another configuration, right? Because you have the...
No, patch size has to be 8. Like patch size is dependent on what clay was trained on. So by default, it would be 8.
Okay, so yes, and as correction to what I said, the image size is not the resolution, the semantic resolution. The semantic resolution is the patch size, which is always the same. It's just the image size is how many of that units you want to have.
Yeah. Cool. And then a few other things. So there's a logger. Now we are using 1 dB for logging. If you don't have 1 dB, just comment this out. You could use CSV logger that would log things to your local. And then there are a few callbacks. We're using a model checkpoint callback that stores your best model, the top two models, and the last model as well. Cool. Yeah, that's it. That's mostly the configuration file. Now let's run, and while it runs, I'll explain you what the code does. So again, we'll go to the README. Yeah, you update the logger with your credentials if you have 1DB, or else just switch to CSV logger, and then train the model, which is this file. I'll just do this. So you do Python segment.py fit config, pass in the configuration file for your segmentation task here. Cool. We get an error. You can delete the previous config file. Okay. Okay, I was doing an experiment before, so that created a default config.yaml, I think. Yeah, I just need to remove it, or I can pass it as an argument to override.
Now, this
Let's
is
just remove it
perfect.
for
The
now.
more errors we find, the likely these errors are the same for the people watching. So it's great to
Yeah.
troubleshoot.
Cool. Let's restart. Okay. Cool. Okay. So the model training started. Now you can see it will take us 26 minutes, 25 minutes to run this, because there are 40 times 1500 is around 60,000 images. We don't want to wait for this much. We shouldn't wait for this much time. So I'll stop this. We'll remove the config that it created. Okay, and we can limit this, right? So we can go to our config.yaml, and here we can pass limit train batches to 50. So 50 times what is, so 2000 chips. Limit val batches to 20, so 800. So we have 2000 training chips, 800 validation chips, and let's restart the training. This is just to show that you don't need a lot of data. You don't have to wait for 30 minutes. You can always still train it for 30 minutes and get better results, but you don't really need that much data. We'll treat it on a smaller subset for
Are these
5 minutes.
batches always the same on every epoch or randomly?
So when you limit the batches, they will be the that's it. I don't know. Like if I set this on Lightning, that's a good. I don't know this. We should probably look at the API, Lightning API.
It's
to
fine either
see.
way, but it would be both cases have their advantages and disadvantages.
Yeah.
But-
If it's random, I think it's better. If it's not, yeah, I don't know. Like I need to see like how Lightning
But
internally handles this.
if it's not random, it will train faster. But if it is random, it will be better results,
Yeah.
I think.
True. Okay. So now it's already training, and you can see the F1 score. For training went to 0.779 in 50 seconds, right? So let us keep it training for a few more epochs, and then we look at the loss curve, right? So
And the intersection over the union is 0.65, which is
no, it should
okay. It's
improve.
good.
Yeah. Yeah. So yeah, you can see like the loss going from 0.83 to 0.18, right? And the
So,
IOU
and the IOU is the higher the
going to
better.
0.81.
Intersection over
Yeah.
the union is how much your target labels overlap perfectly with the generated labels. So an intersection over union of 1 is the perfect one, right?
Yep, it is it's but yeah, it's right now we have like 0.85 of IOU and 0.91 of F1 score, with a small subset of data with one epoch, right? So we'll look at what the model results look like, but while it trains, let look at the code. Like what's the code for segmentation? So for segmentation, this factory.py file, which basically takes the clay encoder. If you look at, let's look at the init, right? In init, we um, get the encoder from clay, right? And we initialize it with whatever parameters it was initialized with. With this, we pass an extra parameter called feature maps. If you remember, like we had feature maps in here. Now these are the intermediate layers. So in case of clay, we have 12 layers, right? So you say, okay, which intermediate layers you want to extract the intermediate features for to do the segmentation task. So this is what it means. And then we do a little bit of hacky code here.
If I
To
can,
basically,
I don't know if this helps others. So basically it's a unit. So it goes from the whole input, the whole thing, to down to the embedding of basically one dimension. And to do that, there are several steps. So when you pull from different heights, you're basically pulling from different abstractions towards that reduction. And that seems also logical, that is critical to do segmentation, because you don't only want the summary of everything, you also want intermediate steps to figure out where things go.
spot on. The only difference between a unit and a clay is like a unit goes from, let's say, 200 to 100 to 50 to 25 to 14, right? But clay or any VIT model goes from 200 to 14 in the first layer. So it will be 200 to 14 and then 14, 14, 14, 14, 14. Right? So you have to
Oh, I see. Okay.
do this, right? So this basically takes that 14 and upsamples it back to 100, right? Takes the 14 and upsamples it back to 50. So you want to create that
Okay.
structure for something like a VIT to work.
Okay.
So this is basically inspired from SegFormer. So SegFormer has an architecture that's hierarchical, and they use this technique. So this is mimicking SegFormer, but is mimicking it on top of VIT. So you do that, and then you pass that in. So you get your data cube, which is Daniel showcased. It has pixels, time, lat long, ground sampling distance, and the wavelengths, right? You do a patch embedding of that. You add encodings, time, lat long, everything. Then you pass it through the transformer layers, okay, which is the attention and the um, MLP layers of the transformer. And for the feature maps that is mentioned by the user, you extract those intermediate layers and create that feature pyramid network for you to do segmentation. Now, this is all the internals of Clay. You don't have to worry about any of these because this is hidden. So what you need is, so you look at the segmenter class, right? It is an encoder, an upsample layer, a fusion layer, and a segmentation head. Your data cube goes through the encoder. It gets all the features, upsamples it, fuses all the features together, and then passes it through the segmentation head to get your logics. Now, I showed you the factory.py file. You can look at it, modify it if you really want to modify your segmentation logic and all, but you don't really have to. If you look at the Chesapeake model file, it takes the segmenter, it passes number of classes, the feature maps, and the checkpoint path, the base checkpoint path of Clay. That's it. That's your model. Okay. Then you specify your loss function. In this case, we are using a focal loss, multi-class focal loss. For metric, we are using F1 score and IOU to measure the metric. The forward is pretty simple. It just passes all these things to the model. Then this is we're using AdamW as the optimizer, cosine annealing with warm starts as the scheduler. Yeah, everything else is like standard training logic. So if you want to do segmentation with Clay, you modify this file, the Chesapeake model.p file, to your dataset, where you change the number of classes. In case of your segmentation task, everything else can stay as is, and your model should still work. Okay. There's Chesapeake data model.
If anybody is actually going to use this for their work and is willing to let us know, we'll be very curious to hear what's going on with the model, who's using it for what. So if you can even just, without much details or something, let us know if you're using this, and also let us know if you have questions. And we're willing to help people on GitHub or also otherwise to get over blockers they might find. They're also important for us to understand what works and what doesn't, where problems might be for users.
Yep. Cool. Okay, then going to the data module. Now this is specific to your data. Now, in case it's just big wave, we are storing it as .npy file. So this is pretty standard. You have that item that reads your chip directory, reads an index, vectorizes the numbers from. So it has numbers going from 1 to 15. You vectorize it to 0 to 6, and pass that is from the data set. Then you define a data module. This is something that is only required if you're using Lightning. So Lightning has this concept of data module and model module. So you need to do this only if you're doing Lightning. But these are like standard ML stuff that you do to load your data, to load your model. That's it. We'll stop it. So it has ran for I think 7 epochs, and we are getting an IOU of 0.87366. Right. Let's look at the loss curve again. Uh, so the val IOU is going to around 0.877, and the F1 is 0.932. Okay, in 7 epochs, and you can see, right, like it's the first epoch where the model went from 0.83 to 0.18, right? So that's when majority of the learning happened, and then after that is just optimization. Now you can optimize it for as long as you want, and the model will become slightly better. But I think for like whenever I have to train a model, if I get something like this in less than 10 epochs, like less than 5 minutes or 10 minutes, I'm good, right? So now let's
And
look
this was
at
also
checkpoints.
with just 50 batches, so you could also do it with the entire thing.
Yeah, so let's use this one, which is the 7th one with IU 0.877. We'll use that, and let's look at what the inference look like, right? Okay, under segment we have a GCP inference.py notebook. So here we get the segmenter from GCP model, the data module, and everything like basic type, PyTorch, INOPS things. We define our checkpoint path of the model that we just trained. I'll replace this with the one after 7 epochs. I'm getting a score of 877, right? So the clear checkpoint path is still the same. My metadata is still the same. Training chip directory, training label directory, blah, blah, blah. Give it a batch size, give it number of workers on the platform. Then get model function basically loads the model. Get data function loads the data module, goes to the validation data loader, gets a batch of data and returns that. And run prediction basically passes that batch through the model, interpolates the output to size 224. Like right now, the model is generating output at half the resolution, so it generates output at a resolution of 112 by 112. So you interpolate it to 224 by 224. And then you do some post-processing like denormalizing the images, plotting it, and stuff. So let's do that. We load the model. It's taking some time. Okay, we load the model, we load the data, we run the prediction, post-process the results, plot the predictions. Okay. So the first row is the image. The second row are the actuals, and the third row are the predictions, right? So trained for 5 minutes for 7 epochs, and I think it does decent, I'd say, in terms of like generating the segmentation masks. Yeah, so that's That's like clay segmentation for you. Feel free to like try this on your system, try it with your data, try it for longer duration training. And then there are a lot of other things that we could do, like using adapters, using LoRa, that we'll discuss later. But yeah, I'll stop the segmentation workflow here and move to regression next. Feel free to like
Yeah, we
ask
are.
question.
Yeah, we are time check. We are 20 minutes on the second hour. So, and this probably is the longer to do. But yeah, if we can switch to the other two ones. We can
Sure,
go.
yeah.
I mean, I can go a little bit over the Q&A, but hopefully we don't make this video like 3 hours.
Sure, yeah. No, I think the other two should be fairly quick. I know that we know the workflow. Everything else has like a very similar workflow, right? So for regression, we are using data from Biomasters. So Biomasters was a challenge that was hosted on Driven Data last year. And you can see like you can look at the results, you can look at the leaderboard. The scores are around 27, 28, right? And if you go like top 10%, it would be around 30, 31, right? That's what it is. You can look at the code. You can look at how they achieve this. But we use this data to test if Clay could do regression. And this is estimating above ground biomass from Sentinel-2 and Sentinel-1 chip. So for this, we have a very similar workflow. So we have our data. So let's look at the data, biomasters.
While you put that also, this regression example for biomass is also exactly what we did with another nonprofit called C3s, and for California, and we achieved 0.93 R square between our biomass, inferred biomass, and their calculations.
Yeah. So if you see here, so we have the NTZ files for our data and TIFF files for our ground truth. Okay. Now the challenge basically has both Sentinel-2 and Sentinel-1 available. And the good thing is to Clay, you can pass both Sentinel-1 and Sentinel-2. I saw there was a question on YouTube where someone asked, can Clay be used with Sentinel-1 SAR data? Yes, it can be, right? But based on the experiments that we did, and this is something that we were trying last week. So I initially started the experiment with just Sentinel-2, and I got to a score of around 31 after 20 epochs. Okay, and which is really good because we so this has like data as time steps. So for a particular place, it has data across 12 months, right? Now Clear doesn't take time series as input. So what we did is we took average of that to create one single chip. So basically losing out like 90% of the information. We're just creating one chip out of it, and we're just using Sentinel-2, and we're just training it for 20 bucks, and we get to a score that's good enough. That's in the same ballpark as like the results that were there on the challenge. Now the challenge has results like 27 and 28, but you should never aim for like very high accuracy because then your model becomes too optimized for that. That's true for challenges. When people are participating in challenge, they would like to win it, and there's mixture of experts and several techniques that you adapt to win that particular challenge. But with Clay, we are not doing anything that's very specific to this problem. We modified the data to a format that can be fed to the model, and then we picked a loss function that was similar to what the challenge had, and we were able to like get to a decent score. Again, now the regression is very simple. We have a factory.py file, which is exactly same as the segmenter. It takes a feature maps. Okay, it creates the conv layers, and then there is a regressor, which basically passes it through the encoder, gets the features, fuses those features together, and then passes it through the segmentation head. Okay.
Yeah, this should really be one file because it's 90%
This
the
should be
same
a
as the
one
other.
file. Yeah. But because we're doing
Trying
two
to
experiments,
centralize.
Sorry, then.
Yeah, just that, like it's literally the same file. We should put that somewhere in central and import the same thing from both and do just a small adaptation. But we didn't have time to do this kind of thing, but just to say like this is literally basically the same model.
Exactly the same file, yeah, true. Now, if you look at the biomasters model.py file, it's very simple as well. It has a model, right, which is the regression, the loss function. In this case, we're using RMSE because this is a regression task, and the forward function just passes the data. This is a similar format to the model. Let's run this. We'll do exactly what we did. So Python is a segment. We do regressor.py. We want to fit. We want to use a config file, and the config file is regression biomasters.yaml. Okay, before that, I need to remove the config.yaml. Fit config configs regression biomasters. Okay, let's start this. Cool. Yeah. So let it run.
That's so interesting because you're doing regression a different way than actually we did it for C trees, which I guess worth explaining really quickly. You are doing the same. You're reusing, as you are commenting, the same process of segmentation for regression. We didn't do that with C trees. We took the embeddings. So we created embeddings, and this is something that I love: embeddings for many applications. And in that case, we forgot about the model. We just did the embeddings of everything, and then we put just a layer, so forward layer, just a very simple net, or you could even do it with a random forest of the embeddings to make a regression.
Yeah, so the difference between that and this would be like in that case, like it would be a single number for a chip that you're predicting. But in this case, you're predicting a number every pixel. So you're estimating
I see.
the background, the ABGM score for the chip. You're giving a number to each and every pixel. So it's like a segmentation regression task rather than a regression task.
Yeah.
If you have
so
any
I guess
regression
if
task,
you have So a regression of the whole image to a number is you can do some embeddings, but a regression of every pixel to a number is this way. Okay.
yeah.
Yeah, and one is like closer to classification, and the other one is closer to segmentation, right? Like in one, you care about the map, right? Like you want to, for each pixel, map what the biomass is in each pixel, and the other one is more like you want the average number or the global number for a chip, and that's similar to classification. Like, is there forest in here? Yes or no? Is a similar question to how much forest in one number, and then where's the forest versus how much biomass is in the forest is a mapping exercise, and they're more similar to each other. So that's kind of, I hadn't thought about that much before doing this example, but I realized like, regression in this sense is almost like a one-class segmentation where you don't use a single yes or no answer, but you basically use the range of the output as your scaling factor. It's
It's so
really
cool. We have one of the organizers of the Biomasters data, Henrik 80, and in the chat. So he's keen to know what number we get.
Cool. Yeah. So yeah, I'd break the mystery. So we are getting a score of around somewhere between 30 to 31 after like training for 33 bucks. That's what we tested last week, but we are using like I think just like 5% of the data that you have. So maybe if we optimize it, maybe we would go higher. But yeah, that's not something that we probably doing, but for others to try, like take Clay and try to optimize it. Cool. So I just wanted to show you the config file for Biomasters. It's very similar. So you're using same feature maps to specify your training directory, your validation directory, batch size, number of workers. You can limit your train val sizes. I didn't do that. So we have like 864 batches, and it takes around 4 minutes an epoch. But within 4 minutes, you can now see like score is already going down to 30, 34. So yeah, so we could let it train for some time. Yeah. Is there anything else in here?
There was while the training happens, Robin was asking about object detection. Yes, it's the fourth class, I guess, of the main classes. We don't have an example yet, but and I believe the code might be similar the way you're doing the feature maps,
Segmentation.
right?
Yeah.
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 For object
For
detection, yeah, for
detection.
segmentation.
Yeah, for object detection, you have a similar workflow. So what you need is basically feature maps coming from the model. Once you have the feature maps, then you need to attach a head that does detection rather than segmentation. So that would probably come next. So we don't have an example of object detection yet. Cool. So if you look at the loss curve, already like this is the first epoch, you can see like it went from 80 to 40 and going down after one epoch. So yep, let's
I don't
run
know
it
if
for 1 more minute.
I don't know if Andrea
Yeah,
Narcetti, the co-organizer, is impressed with this number or not, but that's what
yeah.
we get.
Yeah, one thing we've been discussing here also when we looked at these kind of numbers is would be interesting to look at the generalization capacity of these models. So since this is like the base of our estimations here is trained on a global data set, the base knowledge of the foundation model here of play is it might be better at generalizing if you move away from the location where it trains the regression head, or maybe do better at comparing across time. This is
Yeah, we
something.
haven't we haven't
But
talked about any of the why this is amazing or why this is a different way of working. But yeah, it's basically what you're saying, that we trained with so much data that ideally has a lot of concepts already baked in.
yeah.
Yep.
So even if it isn't as high as the winner of the competition, I
Hey, it's
personally
20
want
minutes.
very often. Huh?
It's only 20 minutes. I'm pretty sure we can beat this.
Yeah, one thing that I probably want to highlight is like the way the learning happens, right? Like most of the time when you build a model, you have to train a lot of parameters to to get the baseline or the benchmark of the challenge, right? Here you get to the benchmark or the baseline like in under 5 minutes and one or two epochs. This for segmentation. You can see a similar pattern for the segmentation regression kind of problem. And the thing that we are trying to test, and this is true for classification as well. So it learns pretty fast, like the generic concept that exists in the imagery, and then it tries to optimize. Now, the optimization could happen at multiple levels. You could unfreeze the entire encoder and let it learn better. You could attach adapters and inject information rather than just extracting feature maps. You could attach LoRa that does feature modification by default. So these are things that you could try further to improvise on the model. That's one style of modification. The other style would be like modification specific to the problem statement, like let's say biomasters. This is a challenge that we want to beat. Then we probably want to like spend a lot more time picking the right loss function, picking the right score, picking the right augmentation, and making changes to the code that is specific to these to make it work. That would be a different problem altogether. I don't think like Clay would get into that, but that's something that people should try and explore
Yeah.
And share more.
Okay, let's go to the third one, to the, what was the classification?
Yeah, while this is training, I have let's okay. I can show you. Okay, let's stop here. We have one checkpoint. Okay, so okay, let's just look at the results. Okay, So we have one checkpoint. Let's pick that. It's not great. It's after one epoch. 0. We'll load the model.
Again, all of the code we are using is in the repo, so you shouldn't need to type anything.
So the first row are the images, the Sentinel-2 images. The second row are the actuals, and the third row are predictions. Now you can see
They're
like
pretty good.
we are getting there. We are getting there.
That's really
They're
good.
over predicting in a few places, but yeah, maybe a few more epochs and they would become better. The other thing that you notice, I don't know if the screen resolution is good enough, but if you see, right, the actuals are at comparatively higher resolution than the predictions.
Yeah.
Okay.
Yeah.
And that's because like the actuals are at resolution 224 by 224 or yeah, or 256 by 2, I don't remember, but one of that. And the predictions are getting generated at half the resolution. Okay. And then you
Why?
upsample it to this. That's how like the current fusion architecture is designed. You can modify it, you can attach another layer and that would generate it at native resolution. But for now, like that's what we have done. Nothing specific, you can modify it. Just it gives you
Oh
less
yeah,
parameters to play.
what I was going to say is that for a competition, we can tweak and do the stuff.
Yeah.
For an operational dependency, what I would do is I would do all of these ones, and then I would figure out which areas have the biggest losses, and then you can either fine tune for those or do other methods. That's something I found the case is that it's completely different approaches when you are trying to win a competition and you're trying to make operational decisions on how to overcome those difficulties. Sometimes it's not training more, but maybe training in other places that only the places that have the bigger losses. But yeah, let's go to the last
We'll go to
one.
the
Yes,
last one,
again,
which is the classification.
the intention of the notebooks and examples here is really to show how to do it, not necessarily to train the best model or something, but also how to do it with real data as reproducible as possible. So that's why we included the data pre-processing scripts in a hopefully convenient way if anybody wants to try. But as an example, the regression model, I think the raw data is a few hundred gigabytes originally. And so it's still a heavy lift to go through all of this, but it can be done and reproduced. And so that was the idea, to basically provide people a way to see code that does these different application types and have some real world examples to show that it actually does what we hope it does. And then folks can take it from there. So if people have improvements again, also there, it would be great to get feedback or pull requests if somebody can tweak this and say, oh, this works even better if I do this and that, then by all means, you'd be most welcome to share that and for us to hear about it and merge it into the code if possible even.
With more than 200 views already, let's go to the last example and then questions.
Yeah, so this is the classification example. This is an Eurosat dataset, and this is like the most simplest implementation. So if you look at like Eurosat current benchmarks, you can see like the best model is getting an accuracy of 99.24, which is just crazy. It's in 2024. But if you go a little back, let's say 2021, 2022, like there's still papers that were getting score of 97.5, 98.14, right? So we typically aim for 99, but if we get around 97, 98, we should be happy. If we get to 97, 98 in 5 minutes or 10 minutes, I think that's a easier lift than building a better model that
Hey,
gets 98.
ResNet got 99.2 in 2019. ResNets are amazing.
Yeah, true. Yeah. But the point being, like, it's good to have 99.2, but you should
Yeah, of
be
course.
happy with 98 because that's what we got, and that's what will be seen now. But the workflow is same: clone the repo, create the environment, activate your environment, download the data. In this case, you don't have to download the data. We are using .geo. And if you run the classify.py script, .geo will check if you have the data or not, and it will download the data for you, right? Again, you download the model checkpoint from Hugging Face, store it in checkpoints, which you have already done. You define your batch size, your number of workers, learning rate, number of classes, right? If you have a logger, you specify that, and then you run this. So remove the config.yaml, and I'll run this. This should be pretty fast because yeah, it has no moving components. Okay. If it starts training, we can look at the factory function for this. Cool, it started training. So let's look at the factory.py file. It is a classifier. It takes the clay encoder and then defines a head, right? There's no feature extraction. And the head is pretty simple. It has two linear layers and a rel1 dropout. That's it, okay? So your forward function basically passes through the encoder, gets the embedding. Now this is similar to what you were saying, Bruno, on C trees. And it takes the embedding, removes, gets the first token, which is the class token, and then passes it through the head. That's it.
So we could use this not with the input, just with embeddings. Like imagine we have
Just
already
with the
the embeddings
embeddings,
for
yeah.
these places. Like if we already have the embeddings, it would be much faster because you don't need to create them.
True, yeah.
Right?
If you already have the embeddings, just pass it through the head. You don't need
And
to
it's
pass it through.
exactly the same because what all this does is freeze the encoder, put a layer. When you freeze the encoder, you're basically making embeddings. I guess the only difference is that we don't do the average of the patches.
We are not doing it. We are just getting the first token.
Yeah. So this
class
is
token.
better in the sense that we put we put the head on top of the model, and we don't do the average of the patches
You
like
don't
we
do
do
the
when we do embeddings.
Yeah. Okay, then look at the model file, which is very simple. You just pass the model, how many classes it has, what kind of problem it is, your loss function we're using cost entropy. Yeah, there's nothing more in here. There's the data module which loads the data. Yeah, and we can look at the loss curve. And let's see how much time it takes. It takes like 20 seconds an epoch, right? So if you train it for 2 minutes, you have 10 epochs. And you look at the score step, right? Like after first epoch, you are at 93, right? And then, yeah, it gets to 97, 9766, 97.6 after 5 bucks. So we'll see if it improves further. Yeah, 98.4. I've trained it for like 20, but I've never seen it go to.
But we can, I mean, if you wanted to go to 99, which is not the point of this, there's a lot of hyperparameters to train to do things differently.
Yeah. And unfreeze the encoder.
Or you can also unfreeze the encoder. Yeah, I guess the only, so we haven't done location. We haven't done the use case that Robin was mentioning of object detection, but the thing we implicitly have covered is how to create embeddings. Can you quickly just do an example and save those? Because I think it's something that people might want to do, how to just run Clay and save the embeddings.
For the Euroset challenge?
For whatever, just how do you save them? How do you create embeddings to save them? And remember that you can do this with the non-technical build one once we release the app. But if you just want to create embeddings, how would you do that?
So if you just want to create the embeddings, there are two ways, right? One is like you could if you're using Lightning, in which in our case we are using, so you could write a predict step function that would just load the best checkpoint, pass your data, get the embedding, and save it as. And we have tried saving it as a GeoParquet file, so it stores like your embedding along with your meta information. That's one way of doing it. The other way is like compiling the model. So you could save it as a compiled PyTorch model, and then that becomes very portable for you to run. Unfortunately, right now we are not able to like create a portable version of this model because we are using INOPS and multi-head attention and dictionaries for data loaders and stuff that and we are using branching in our forward function. Now these are stuff that make it tricky to do torch JIT compile. So you need to remove all of these to create a scriptable version of your model. That's not there, but if you want to create embeddings, I think there's already code there. We had it for V0. We just need to
Yeah.
recreate it for V1.
Just basically do the predict. Okay,
Predict,
so it's 15 minutes for the 2 hours. So I guess we should just jump in on the questions. Before we go into that, we did not explain anything. Just if you want to know more of who we are as an organization and why is it a non-profit, you can check the non-technical webinar where we go over those. Basically, we are a non-profit. Everything we do is based on our founders who gave us philanthropy money. We are a 501c3 in the US. So everything we do is completely open source, completely open data. And the whole idea is for non-technical users to provide an extremely easy way to explore Earth observation with the 2 web applications that we are developing. And for technical users is to literally give you a multi-million-dollar model on day 1. So you can do whatever you want with that. And that's kind of the theory of change that we want we have put a lot of work to training, and you can ask questions how we train it. It was a pretty geeky experience to train B1. But yeah, that's what we do. You've seen it. We haven't talked about architecture. If you can see the documentation or ask questions about the architecture. That's the what we do. The how we do it is a non-profit, and the when we do it is now, because we believe there is an outsized opportunity to influence how we do AI for Earth with these foundational models. Should we go for questions? Or Soumya, whose screen is this?
Sorry, I was on mute. Really, really quick. We have pull request open made by Lily, another tech leader that works on the project. So we internally, like, or when we do run the model, we store embeddings as contiguous arrays in Parquet tables, essentially. So I don't know what's down here. So this is a convenient way to store embeddings if you're running them at scale, is to basically take these like fixed size arrays and put them into Parquet files, and then you can group them. For instance, all the embeddings for a larger image, you run through it and you put that into one Parquet file. So, for instance, one Parquet file per night scene or sentinel scene is a good way to do it. But this is also a longer discussion on like what are good standards now and in the future to do these kind of things. We're currently just as a side comment, we're currently putting embeddings as rows in Parquet.
Yeah, there's a discussion of Chris Holmes and others to what's the format to do for these ones. We want to generate a ton of embeddings because we believe that a lot of the things you can do it directly, like Soumya was showing, but for a lot of use cases, the embeddings are really good, and that's why we want to create embeddings. And we are really keen to know what the community decides the format for doing these things. Thank you, Daniel. I have a question which Robin asked, but it's slightly different. So Robin was asking about experiments for change detection. You've shown one with the principal component analysis, but for segmentation, I always wonder, can we make a fake instrument where we put 2 sentinels before and after, and then we do the segmentation of the thing that changes? Or how would you do change detection and segmentation at the same time?
We've talked about this before. With
Sorry, Daniel, go ahead.
same. Well, I'll take my high-level view, and then if I get it wrong, please correct me. But one thing we said is that basically doing a combined input with more like double the bands to the clade coder would not be the best choice, because it's a bit confusing, and it hasn't been trained to find differences. Like, it's going to assume all the input is from the same date from the same place, right? That's how it's been trained. So it would be better to basically do what we did in segmentation, to pull out these intermediate layers for the two images, and then make a head that takes kind of those intermediate embeddings as those you can stack together and make a head that gets basically these intermediate layers from both images, and then looks at finds differences in those. But the model itself has always been trained with imagery that is consistent. Like, it's basically more bands of the same place at the same time. So if you start inputting data that isn't coherent between each other, I don't think the model will magically pick this up, but it can always be tried out. So I don't know. I think that was what I understood from a discussion on this topic.
Yeah, that's very interesting to take the feature maps and then connect the feature maps and the embeddings with a head that takes care of the change detection. So basically you split in the first segmentation and the change detection concatenated. Right, Soumya?
Yeah, I agree with like whatever approach that Daniel described. That seems the way to go.
Yeah, one of the things that we didn't have time to do. So when we train, we take an image, do the training to reconstruct the image, and then we compare how good that is. One of the things I wanted to do is be a little bit more creative and then ask it to reconstruct another instrument or another time, and then to try to force the model to pay much more attention to the location or to the time. But yeah, we didn't do any of that. So as far as we know, the model is not really paying much attention to the actual location or the actual time, because that's something that doesn't change in the training. That's my thinking. I don't know if Daniel or Soumya or Laura disagree.
Yeah, we actually, like, in some cases, I forget which one, but in some of the training data we used for the examples here, we don't have the location and date. Actually, I think the Biomasters one doesn't have location or date. So we just input a fixed location and a fixed date, and it still works. So I think that's one indication that the model doesn't change its output too much based on the date and time and location. But we haven't quantified this. Really. But it works really well. So basically the message is, if you don't have the location and or the date of the imagery you're using, that's fine, just input zeros and you'll still be okay.
There was someone, we will not go because there's 10 minutes left, but there was someone asking about the architecture. So I'm just gonna show on the screen, this is the architecture. And it's basically two main transformers. One is this guy over here, which is instrument dependent only. It does not see the content of an image. And all it does, it takes the input of that parameterizes the instrument, like the number of channels, the wavelengths, the resolution, time, all that stuff, and then learns how to patchify, how to make patches of the content of the image. And then the other guy, which is this transformer here, basically that's the usual thing, the mask autoencoder, transformer, all that stuff. There's a couple of, and then you go the opposite way in the decoder. So this is where the embeddings are done. And then you go the other way to decode the image, and then to depatchify the instrument to get the reconstruction of the image. And that's how you get the reconstruction loss. There's a tweak, which is that besides the loss of the difference between the mask autoencoder normal, as many models do, we also use a frozen encoder with Dino and compare the loss of the embedding using Dino to the embedding using our model. And we do this partly to have like a universal anchor across instruments, and this is only like 5%. Did I do a good job, Soumya, describing your child?
Yep.
Maybe also it's a good moment to highlight that a lot of the ideas that went into this model came from other existing publications. Soumya knows them best, but maybe if you want to just give a shout out to the ones that we.
Sure. Yeah. Yeah. I think like yeah, we we were super happy to have like build this model at a time when a lot of the research labs were already doing a lot of the work and already publishing. So the unique thing which handles like the one thing that handles like images of different bands comes from DOFA. So they have initially defined that architecture. So great work, great labs, and you should look at all the papers that they publish. They recently had a paper published on benchmarking foundation model. Again, a great paper. So great work from there. The idea of embedding time and lat long comes from SATME and ScaleME. The idea of using a pre-training teacher network comes from the team at Medita and their paper. Yeah, and then the other man-related tweaks that we did internally at Clay, but it basically like building on top of all these papers where they have invented these cool small new techniques. We just like brought all of that together and like created one big piece that then like helped us to train the model easier, faster, and at a larger scale. So a big thank you to all the authors of those papers.
Okay, questions from the team. How would it be to use PlanetScope or Satellogic? What would you need to do?
For training on PlanetScope, I'd say like because the model has already seen like high resolution, like 50 cm 1 meter and 10 meters and 30 meters. If you pass PlanetScope, which I guess varies from 3 meters to 5 meters with those wavelengths, if you pass that in, Clay should work out of the box. So yeah, please try that out and let us know
But
how it performs.
so I think the steps is that you will need to go to the specifications of the instruments and add one in the JSON file.
Add another,
add one, yeah, which is, I mean, it's not that much. It's I think PlanetScope is 4 bands also, so red, green, blue, near infrared. Put the numbers of the wavelengths, which is not exact. Probably it doesn't really matter that much. The resolution, so the resolution of the instrument, not of the image. I guess if you use different images with different nadirs, it would be different. But yeah, that's the one. Yes. So that's we have actually one of the things we can do is that if people send a pull request with Satellogic or PlanetScope or something, we can just put it all there because it doesn't really matter that we have instruments that we don't use. LINS was not used in this stuff, and then it's easier. It should work. Yeah, exactly. I'm very confident that it should work for Planet, for Satellogic. I think also it should work also for Umbra, even though Sentinel-2 synthetic aperture radar is much lower resolution. I will be keen to know if it works.
Yeah, so basically here, I think the 3 numbers you need for each band that you want to input is the mean and the standard deviation of the pixel values of the data that are going in, such that the model can normalize the values. And then the wavelength of the band, the central wavelength of the band that it was used, or of the optical sensor. And then these RGB indices are just to train the model further. So if for the Dino training teacher setup, we use these bands to pass the Dino essentially. And then the band order is also for it to internally know how to map the mean and standards to the different bands when they are input. So this is something like if people have this information, then just add it here and reference it when running. The other thing is, as I said, or also Bruno pointed out, basically the wavelengths here, they're relatively similar between the different satellites for red, green, and blue, and the standard near infrared. So if it's just RGB imagery and there's almost no information about what is in there, night is a good starting point.
What would you do? This is something we talked about it, and we didn't really do testing, but what would you do if you have an instrument like Landsat that has RGB, but then also a pan band? Would you do another instrument for the pan version, or like, I don't know, how would you do that? Because so the pan band is much broader wavelength and usually twice the resolution.
Yeah, that's a good question. I don't know. I would use the central wavelength of the pan band. Ideally, I think we could eventually make this instead of just one central wavelength, the start and the end, right? So the bandwidth of what you're looking at could be another factor, but we haven't trained it with this. So a band like the pan band is harder because it's not very narrow around one wavelength. It's a big range. That's called panchromatic. And so there, I would just try something. It would be trial and error. My best guess would be to use the central wavelength of the pan.
Also, the resolution is different on the pan band.
Yeah. Well,
so we hear
downsample accordingly.
Yeah, you could upsample, but here, so the way we could do it right now, which should maybe change in the future, is the ability to put different resolutions for different bands for these cases.
Yeah, but that's not possible right now. So all the bands need
Yeah.
ground sampling system.
More questions. How long did it take to train B1? This is, I believe, this is all on the documentation. If I remember correctly, it was 70 million total chips on 36 H100 for 4 days, was it?
Approximately, yeah.
Yeah, so that's the question, to do that. We could have trained more. We could have stopped. Do you have the 1 dB of the losses for that run to show if it was stable, or we deleted it? I don't remember. Or maybe it's in the documentation.
We have, let me find, like it's not deleted, it's there. Let me just try and find that out.
And the actual locations of all the stuff we did for the sampling, it's also on the documentation.
On the documentation, yeah.
Okay, while you do that, another question. How much CPU memory do you need for fine-tuning? Oh, we talked about this a little bit. Like, we've done it with 390s and 4090s, so NVIDIA GPUs, 810s and H100s, and with CPUs. For inference, for CPUs. For fine-tuning, I don't know if we can fine-tune with CPUs, but yeah. I don't know if others wants to say more about the GPU.
It's not much. Basically enough for the model to be in there. For the classification head, for instance, as you've seen, that's a two times simple linear layer. So that's really, really tiny compared to the model itself, which is a bit bigger. So I think, if you have enough memory to load the frozen encoder, then you just need a little bit more, because the whole idea is that the classification head is comparatively small, and so that wouldn't take a much more memory. And so, I would say with a few gigabytes of RAM, you should be able, or GPU RAM, you should be able to do some fine tuning. Yeah.
Okay, so there was also another question.
The factor is actually the batch size, and I think that's probably the more important one.
Yep.
So if more memory, then you can make a bigger batch and run through your data faster. So I think actually I got this wrong. It's less about the model size and much more about how much data you can pass in time. But
So
again, like with a few gigabytes of RAM, 8 gigabytes, I think is a good starting point. But then
there is, as far as I know, there is no paper to know the dependency of how is better, more large size or bad sizes or cheap sizes or self-attention sizes. All the stuff does not exist yet for Earth's observation. So it's more like try it out and see what happens. What I would say is that, of course, the bigger the batch, the smoother the curve of the learning, because there's more averaging of the back propagation weights. So you want the bigger also, and also less time to do that. Another question is comparing to Prithvi. Prithvi is a fantastic model developed by NASA and IBM, and they released that, I believe, last year. And I know they're working on a better one. I don't know what makes that new model better. I believe it's more training data and more features. But the main difference is that Clay can run on any remote sensing like Sentinel, Planet, Landsat, all that stuff, and different resolutions. And I believe Prithvi only for HLS, so the Sentinel Landsat archive at that resolution, and also train only on the US. Maybe the new one is trained on the whole model. Architecturally, I think both of us are mask autoencoders, and because they are only using one instrument, they don't need the other transformer we use for being instrument agnostic, and they also don't use the dyno loss. In terms of performance, we have not compared that head to head. That would be interesting to do exactly the same task with for the places we can do it and the instruments we can do it exactly the same. As for training, I would imagine that because we use more training data, the model should know more semantic. It would stand to reason to me, but I don't know. I don't know if that is the case or not. But that's what I see differences. But you, Daniel, and Somia, you work also. You help the team create Prithvi, so maybe you can also shed some light on the similarities and differences.
Yeah, I think like you covered all pretty neatly, Bruno. Like it's trained on HLS data and and also the other thing is like Prithvi takes time series as input, so it takes 3 time steps as input all the time. And yeah, right. Like with V2, they probably like do it on a global scale, so it's more robust as well. And yeah, but again, like great model coming from NASA and IBM, and probably like one of the first models that was like a lot talked of. I know there's like the models like SATME, ScaleME, and Presto that came before, but Prithvi was like kind of the first model that got a lot of discussions and things around it.
It inspired us to start Clay. Another difference is that Clay is not only the model. Clay, our role, our organization's role is not just to create a model, is to make sure or make it as easy as possible that technical and not technical people can use it. That's why we also creating those websites that you can check out in the other non-technical webinar, and that's why we are doing other work and working with partners to apply it. As we go, we also have we do talk about Prithvi, and if people want to use Prithvi instead of Clay, that's fantastic. Clay is not about pushing a model. Clay is about shaping what is AI for Earth and how we can make AI for Earth better. And we believe that there was an opportunity right now to make an effort to make an instrument agnostic model, which we developed. More questions. How is time used in the model? Time is not used in absolute terms. Time is used in, I believe, correct me if I'm wrong, Somia, it was month of the year and time and day of the week, was it?
It's week and hour. So week
and hour.
of the year and the time step of the image that is captured. So that get encoded, and that's what the model means.
And we talk a little bit about it. I don't think the model pays much attention to time or location because we have not instructed to pay attention to that. Maybe it does. That's something we could check and just change it.
It does, but it can also work without it. So there are only 4 vectors in the model. that handle time and this thing. So even if you remove it, you still have a lot of information
Okay.
from the patches, so that exists. If you pass it, it's better because then it has a generic understanding of what things it's looking at across the globe, right? And at what time step it is looking at. But if it's not there, even then the model has enough information to capture because we trained it on like I think 20% of the images, which is zero time step and lat long, so it understands that it won't always have that information.
One of the reasons we put time and location is because I have a dream that maybe V2, we can put an input of the model without pixel data and then ask the model, hey, Madrid 2024, how does it look like? And see how the model is able to memorize, just like sat clip, but on steroids. Like, or take an RGB and ask to reconstruct a SAR, or take a SAR and reconstruct an RGB, or low resolution, high resolution. The idea that a Earth model can memorize Earth itself and the semantics, it's extremely appealing to me. Just like a GPT is able to memorize the corpus of knowledge of the world. But it's not there. So B1, if you don't put pixels, I'm pretty sure Clay is gonna complain. Ablation studies, Somia, for Dino and for the location. We haven't done much of that, right?
We have not done any ablation studies. Like the ablation study for us is like building this downstream task and comparing it with the scores. But if someone wants to like benchmark Clay on, let's say, GeoBench or a Phil EO kind of thing, like feel free to do it. We can help you with setting it up. Maybe Bruno can also help you with the infrastructure to test things out.
Yeah.
But
Yeah.
I don't think we'll have time to do that on our side.
This is an open call as a reward for having watched 2.5 hours of technical discussion. If you're working on testing Clay or working on something that is the output is going to be open data and you are constrained for resources, do reach out and hopefully we can help you do that because it's part of testing and benchmarking Clay, which is extremely important for us. Another question, can you use Clay for images Clay was not trained on, like PlanetScope, Blue Sky, or high resolution commercial satellite? My hunch and my belief, and the reason we designed it how it is designed, is that yes, of course, the closer the instruments you are training to the instruments we train on, the more confidence it's going to give good results. We have trained down to lens resolution, which is an open data in New Zealand, which I believe is 5 centimeters. So even if you use drone data, should work. But it doesn't mean, like, for example, MODIS on the other end of the spectrum. I don't know if it's going to be good on MODIS. It's going to run, but we haven't done benchmarkings on that. I would suspect that PlanetScope, Satellogic, and Maxar satellites would be well within the scope of the training set. Any other question or comments, Daniel or Soumya?
There are a few questions on YouTube. I also have my system
Oh,
open.
yeah.
So this a question from Elizabeth. She's asking, how is this model different from Prithvi? Soumya, I think Tyler,
Yeah,
my
this
colleague.
this one I answered.
Okay. Then is asking, for training V1, the data set was on a local drive streamed from S3. What are the practicalities of working with this large data sets? Yeah, this is a very interesting question. So when we started out, we were initially, like the initial plan was to make everything repeatable with Clay. Like we wanted to have the model open, also the training pipeline open. So the idea was you have everything built on top of Stack, so you could just stream your data in. Like you don't really need an S3, and that's what like Daniel designed his Stack chip library around. So you could have just meta information in your system and create data on the fly. And the initial idea was like we'll use like a high efficient data store, like something like an FSX Lustre store that's on AWS. But that didn't work out. Like when we started training, the GPU was idle most of the time, and it was taking us a lot of a lot of time to just load the data into the system to be able to train.
So, but
So what?
let's double down on where we think the problem was, because I think this is solvable. I think part of the problem is that when you stream, you have to go from the file, hopefully on AWS, down to read the range read and then pre-process or doing the things and then give it to the GPU to load for the whole batch. And I think the biggest problem was that not all the images in the batch arrived in the milliseconds that it will take. So the batch was just hung waiting for like up to 50% of the time for the whole set to complete, right?
Yeah, so this is, I think, the way PyTorch handles its data loaders. So you can have like parallel data loaders, but a single data loader is sequential. So the number of data loaders that you create is dependent on a CPU cores, which can increase, but a single data loader is sequential. If your batch size is 100 and you have 100 data loaders, one data loader is sequential. So one data loader would go, read the data, then go read another data, do it 100 times, and that takes a lot of time, right? So what we ended up doing is like creating like batches as cubes. So we pre-create these batches of 128 is the number that we picked. So uh, each cube had 120 chips in it. So it was 120 times the number of bands times height times width that was stored at once. So the reading time might take longer, but you are getting like larger chunk of data into the system. That helped, that kind of helped us to speed up the data loading. The other thing is like because we had access to these P5s, which are these larger VMs in AWS, they have like really large NVMe stores. So you have like 30 terabytes of NVMe storage, and it's like closest store to your GPU or your RAM. So if you store your data there, or if you could do an async load of data to these NVMe's, then you could just read data much faster and do that. So I do not say we have solved this. There are a lot of things that could be further improved in this pipeline.
It
And
was,
we,
it was a limiting factor in our training. We wanted to train for more, we wanted to train with the testing things. It was a limiting factor because we were hoping to do that. And I mean, it was like 10,000 images per second. That's an insane amount, 10,000 inputs, which is insane amount of inputs per second to figure out. So this is the forefront of what we believe anyone has done, at least in the open. If you had your own cluster physically next to that, maybe it would work, but then you also would need to have the data to stream in the same place. So yeah, there was, I remember there was also other options we thought about, like in the epochs. Don't replace the whole epoch. Don't replace all the data, just replace a little bit a percentage at a time. So then basically you are doing epochs incrementally, like 10% every epoch different, so that you also don't need to wait for a lot of time. But yeah, that was, Robin, that was the thing we did, and we hope to improve it for next time. Any other question?
Andre is asking what are our next steps.
It is tempting, very tempting, to do exactly what we said, to figure out all these streaming training architectures, to do more heads, to do more training sets, to do more like cross different times, cross instruments. I believe that unfortunately for this part of the house, of this part of the problem, we have enough good model that the bottleneck of impact is not the model itself, but the application. So for us, for Clay, the focus in the next few months is not only figure out improving the documentation and taking care of course, the code, but focusing mostly on users and non-technical users. Because otherwise, the universe of possible users of Clay is small. It's us. It's maybe what 2 million people in the world. It's not really gonna do the impact that I believe could come with AI for Earth. So for Clay, the organization, the next steps is not so much on the model, but on the application. And that means the no-code websites and the partnering with journalists, partnering with other NGOs, partnering with the startups, and satellite providers to use Clay, but the model is open and the model is there. So if others want to continue developing, we will continue developing the model too, but maybe at less pace in the next few months than we've done. This started in Christmas last year. So this is an amazing amount of work that Soumya and Daniel and Lily and team done in this short amount of time. Okay, so I think there's no questions. And any closing thoughts, Daniel or Soumya?
I think it's been a long session.
Huh?
It was a really long session. I think we're beyond 2 hours now.
Yeah, 2.5.
Yeah, just a big thank you to anybody that made it so far, but also a big thank you to you, Bruno, from our side. It's been, as you said, a lot of work, but an amazing partnership, and it's been fun to develop, and looking forward to the next steps. Just outlined.
These, I don't know if you mentioned it, but they are from Development Seed, which are the partners we work with for the model.
Also, like things that you'd like to build on top of Clay, like a lot of missing pieces. Like we love to have adapters and LoRa and others built on top of Clay. We love to benchmark. We love to test it out on different problems, different data sets, detection, let's say change detection, those kind of things. So if you have a data, like feel free to create a PR. If you want to like implement it yourself, like do reach out and we can help you out to set it up and think through the solution. So yeah, it's in the open. So feel free to create issues, open PR if you have time.
Please, that would be amazing. From my side, tell you that there is $10,000 on the line for the competition we are running. Go to makewithclay.org and those 10,000 is to help make the best model even better. So if you use Clay or other model and you want to improve it for everyone, then go to that competition for a chance to get the $10,000 in compute for that model. Non-open models can also participate, but they would not be eligible for that. Other than that, we have a working group for benchmarking to work together as a community to figure out what are the tasks we want to put forward for every model to be compared with each other. And yeah, if you're using it, please let us know. And if it works, let us know. And if it doesn't work, let us know too, because that's the best way we can improve it. We know that it's very early, and the more you work, the more it works for everyone else. So thank you everyone who has been for the last 2.5 hours in this live stream. And for those who are watching the recording, reach out if you have questions, and thank you.